Alright, for the last class we finished up our section on the kinematics of particles, and so today we're looking at kinetics. And the first method for looking at the kinetics is going to be with equations of motion. And so the bottom line, Newton's second law, is that the sum of the forces acting on a body, acting on a particle, are equal to the mass times the acceleration. And that's of course a vector equation, but if we're in three dimensions, then we can write that vector equation as three scalar equations. And we're going to do that with all three of the coordinate systems that we've looked at earlier. So to start out with, we'll look at rectangular components. And so the summing forces in the x, y, and the z directions gives us the mass times the acceleration in each one of those directions. A lot of the problems will involve friction. So as you recall from statics, remember that the maximum value that a friction force can have is the static coefficient of friction times the normal force. And when the friction reaches that value, we say that the body is on the verge of sliding. In other words, that's the maximum value, so if you increase the force a little bit, the friction cannot increase any further, and so the body will begin to slide. Once it begins to slide, the friction force drops a little bit. The kinetic coefficient of friction is slightly less than the static coefficient of friction for almost all materials. And so now if it's sliding, you know what the friction value is. It's kinetic coefficient of friction times the normal force. So when you work problems in kinetics, just like in statics, you always have to draw a free body diagram. And so the free just means you're separating that body from all of its surroundings and show all of the forces that act on that particle and label all of those forces. When you do that, you can write your equations of motion very easily just by looking at the forces that are on the free body diagram. Pay particular attention to mass and weight. Remember that if you're working in SI units and you have a body, usually it'll say, this is say a 5 kilogram body. Remember that's the mass. When you need the weight, you need to multiply that by the value g, 9.81 meters per second squared. That gives you the weight in newtons. On the other hand, if you've given a 5-pound box, then that of course is its weight. If you want to know its mass and you're working in feet, which usually most of these problems are, you divide that value in pounds by 32.2 feet per second squared to get the mass in slugs. So here's a typical example problem. You've got a box that's sliding down the ramp from point A to point B. And so in this kind of problem, you want to set your x and y coordinates such that the x direction is in the direction of motion, that is down the ramp. If you do that, then the y direction, when you sum force in the y direction, you can set that equal to 0 because there is no motion in the y direction. And from that, you can then find out what the normal force is. If there's friction involved, that'll tell you what the sliding friction is. And then summing forces in the x direction gives you the acceleration. Now, of course, in a lot of these problems, you're then going to apply what you learned in kinematics to now that you know the acceleration. Here's one of my favorites. This is Pulley Man. You'll see him a lot throughout the semester. And in this case, you want to draw two free body diagrams, one of the man and one of the block. And in this first iteration of this, we say that the pulley is weightless. And what that means is you can turn the pulley without having any kind of unbalanced moment on it. So in other words, the tension on both sides of the pulley are going to be the same, and so the tension in the rope in this case is going to be constant. You also see a very simple dependent motion problem here, that as the man moves down, the block moves up at the same rate. So the man's downward acceleration equals the block's upward acceleration. Take the sum of the forces in the y direction, set them equal to the mass times the acceleration of each, and you solve for the two unknowns, the tension and the acceleration. And again, using the acceleration, you can find either the time to drop the 6 feet and or the speed when you've dropped 6 feet. And again, it's a good one to remember when you draw that free body diagram of the man with the weight down and the tension up, is that in statics, you'd simply say that the tension in the rope is equal to the weight. But that's not true when you have acceleration. If something's accelerating downward, like the man, the tension in the rope is going to be less than his weight. On the other hand, if you're pulling the block upwards, then the tension in the rope is going to be greater than the weight of the block. So when you get done with this type of problem, you should see that the tension is somewhere between the weight of the man and the weight of the block. In the next class, we're just going to continue with more example problems like this. One in particular that will work, we work some problems with acceleration as a function of s and use the a ds equals v dv. We'll show a problem that has a spring involved, and you'll see that because the spring force is a function of displacement, that you'll come up with an acceleration that's a function of displacement, and you'll see the value of using this equation.